Hello, in lab number 5 we'll be working with something called a rotary encoder. It's actually a quadrature, which means it will produce 4 different edges as you're rotating the device. So there's actually 2 channels on the device, one called channel A, the other called channel B. On the kit that we have, it's actually labeled DT for data and CLK for clock. As you turn the device, it's producing pulses. Okay, you can see in this example that channel A is going high, low, and channel B is also going in that direction. Now, what we're able to do though is that as we're turning the rotary encoder, it's actually producing 4 different edges. It starts off by producing a rising edge on channel A, rising edge on B, falling edge on A, and then falling edge on B, and it repeats again. And this can be tested with a counter timer, and we can actually test each of the 4 edges, or we can just test the rising and falling edge of channel A, or we can just test the rising edge of channel A. The more edges you test, the better resolution you will have. This is a screen capture of the picoscope measuring the 2 signals from the rotary encoder, the DT and the clock signal. And I've actually lined up the rising edge of the DT signal, and notice that the clock signal is a logic low every time this goes through a rising edge. So rising edge, logic low, rising edge, logic low. And this happens only when we're turning the rotary encoder clockwise. And that's one of the features that's important with a rotary encoder, is you can determine the direction that you're turning that control knob, clockwise or counterclockwise. And we're going to be able to tell how many degrees we've turned it. Okay, this particular rotary encoder has 20 pulses every 360 degrees. So that's 18 degrees per pulse. And in this diagram, you can see that I'm again using the rising edge of the data signal. And in this case, I've turned it in the other direction, counterclockwise, and my clock signal now lines up with a logic high. So rising edge, logic high, rising edge, logic high. And the same thing follows through. So that's where I'm able to determine that it's turning in a counterclockwise direction. In this example, I'm also measuring the data and the clock signal, and it's taking, at least for some of the turns, about 25 milliseconds per pulse. And there's 20 pulses per revolution. So could you calculate how long it will take to turn 360 degrees? The answer is underneath here, and I'll give you a few seconds if you pause the video to try and determine the answer. The answer is about half a second. I determined that time by measuring or multiplying the 20 pulses times 25 milliseconds. That gives me 500 milliseconds, which is a half a second to go 360 degrees. This is the circuit for Lab 5, Part 1, and you will be connecting eventually 2 signals, the actual signal from the DT pin on the encoder and the clock pin on the encoder. But before you actually connect it to digital I/O 0 and digital I/O 2, it must pass through a debounce circuit. And that's very important if you want to make sure that you're only getting 1 count as it is being turned. So the output of the HC14 will eventually connect to the input of the encoder, and the output of the second HC14 will connect to the clock signal. And these will connect to digital I/O 0 and digital I/O 2 on the MDAQ. These are the encoder pins. This 3rd pin is actually optional at this point. So you must connect in series with the DT pin, a 100 ohm resistor, a capacitor, anywhere from about 0.1 to 1 microfarad will work. Okay, and then you have to make sure you're going through the input on this side and the output on the other side before it gets to the digital IO0 pin. Okay, that's very important. And also the HC14 must be connected to ground on pin 7 and VCC on pin 14. Make sure that those are connected. And you can check these signals with a picoscope. So you can connect your picoscope to that pin and ground, and the second channel of the picoscope to the clock pin and ground. These will tell you that the signals are being properly produced. And what you should notice is that as you turn the device in one direction, a rising edge will show you a logic low on the other signal. So for example, if this is clock and this is DT, a rising edge will be a low, another rising edge will be a logic low, rising edge will be a low. Now, if you do the opposite and you turn it in the other direction, you should notice that a rising edge in the clock signal will show you a high on the data, and that'll happen as you're going through. So that's one of the ways that we're going to know that it's going clockwise or counterclockwise. And the encoder that we're using generates 20 of these pulses per 360 degrees. That's why each pulse represents 18 degrees per pulse. And it'll take 20 of those pulses to go 360 degrees or 1 revolution. This diagram is just trying to show you the difference between the signal being debounced and not debounced. So this happens to be the input signal, and this happens to be the output signal after it's gone through the debounce circuit. Okay, it makes the edges very straight, not rounded, very straight, and it'll remove any pulses that occur during that rising edge or the falling edge to ensure that you only get 1 pulse every time the encoder goes through a rotation. Okay, or 20 pulses for every 1 rotation. This is an example of setting up the software for the rotary encoder. There is actually a DAQ assistant that you will be opening up for the rotary encoder, and it relies on the signals being connected to digital IO0 and digital IO2. So 2 pins on the MDAQ. That's very important. And what you're going to be doing is opening up and configuring the timer counter. So it's going to be a timer counter function, and we're opening up the angular position, and you want to make sure that it's set for actually in our case it's going to be 20 pulses per revolution. The initial angle is 0, the units is ticks, and it's on 2 terminals, and the 2 terminals are 0 and 1. And we're going to use actually X4 decoding. I think on one of the other slides it does show that configuration. So X4 is where it actually measures the rising edge of channel A, that's 1 edge, rising edge of B, falling edge of A, falling edge of B. And then it gets repeated over and over again. But that's why 4 edges are being selected. Actually, this slide shows it a little bit better, that we are doing 20 pulses per revolution, and we're using decoding type X4, and that measures the rising and falling edge of both channels. Okay, X1 only measures the rising edge on 1 channel, X2 measures the rising and falling edge of a channel. So here is a screen capture of the rotary encoder operating, and we're connected to the DAQ assistant, and these are dynamic data type lines, and we're going to show the number of encoder pulses. So what we see here matches up with encoder pulses over here, and the encoder signal is going to be a slider with a minimum of -360 and a maximum of 360. So it should go in this direction, I believe, when we're turning clockwise, and it's going to go in this direction when we're turning counterclockwise. And you should notice that it takes one complete revolution to go in this direction, or 360 degrees. That's the 20 pulses times 18 degrees per pulse. And then when it's going in this direction, it should go up to 360. We're also counting the loops, just very good to do that, to troubleshoot. And we do have a stop button here. Okay, remember that these two signals, after it's passed through the debouncing circuit, must be connected to digital I/O 0 and digital I/O 2. All right, this is my circuit for lab number 5, and you can see here that I have the HC14 and two of my wires, the DT and the data, are going to some pins. Actually, it's wired a bit different than shown in the lab, but that's okay for the demonstration. And I also have a connection to ground and to +5 through the rotary encoder. And then the two outputs from the debouncing circuit are then fed to the inputs. This is D0 and this is D2 to act as the counting inputs. So as I turn my rotary encoder, and I can turn it in a clockwise direction or counterclockwise direction, it's going to be producing pulses in my software. And I'll demonstrate that in just a second. Now we're actually going to look at a LabVIEW program in actual execution. So this is my program, and you can see that I have it connected to digital I/O 0 and digital I/O 2. Those are signals coming from the rotary encoder after it's passed through the debounce circuit. So I'm going to be displaying the number of pulses, and I'm going to do it on a slider as well, and in a couple of different ways. I must have a loop counter and a stop, so those are kind of normal for every LabVIEW program. So I'm going to open up this DAQ assist, but you place that DAQ assist like you would any other, and we can actually just open another one to try it out. So what I'm going to do is, this is my block diagram. I'm going to go to measurement and I/O, go to NI DAQ, and it's probably off the screen, but I'm going to select DAQ assist. Okay, and when you open that DAQ assist, what we want to do is acquire a signal, and this time we're going to go to a digital input, and we want to do position. So we're going to select position, and we want to use linear position. So I've selected linear position. Then I have to select the my DAQ that I want to use, and it's only ever counter 0. So I select counter 0, click on finish, and once you set this up, the way that you want to set this up is make sure that you've selected linear position. You can go to details, it tells you that it's going to my DAQ, but you want the initial position to be equal to 0, and we're going to be controlling. Okay, now we're back at this screen here, and I want to set things up so that we're going to measure in degrees. So what we want to do is set it up for angular position. You can see that I have angular position set up here. And for our particular encoder, it produces 20 pulses per revolution. There are some that produce 600, so much greater resolution, but this is 20. And we want the units to be in degrees, so select degrees. Our input terminal should be defaulted to digital I/O 0 and digital I/O 2. And the decoding type, you have a choice of X1, X2, and X4. We're going to choose X4, no scaling. Make sure this is set to one sample on demand. And actually you can test it out. So if you have your hardware connected, which I do right now, if I turn this, every turn that I make, it should increase by 18 degrees. And if I turn it 360 degrees, I'm going to back to 0. If I turn it 360 degrees in a counterclockwise direction, it goes to -360. And if I turn it in a clockwise direction, it will eventually go to 360 degrees. But what you should notice, if it's properly debounced, every little click that you feel should produce 18 degrees. So let's go back to 0, and I'm going to turn it clockwise. There's one click, second, third, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it worked perfectly. It gave me 360 degrees for 20 pulses. And that's what you should expect to see in the lab as well. So I'm going to stop this. I'm going to say OK. It's going to recreate that DAQ assistant. Temporarily breaks the line until it creates it. And now I'm going to go to the front panel. Okay, and here's my front panel. I'm going to run the program. And it's just showing me the loop count, and right now everything reset to 0 because we specified that in the software. And then I'm going to turn this clockwise. And actually, in my case right now, I'm turning it clockwise and it's going negative. If that happens to you, just switch around the two lines, the DT and the clock, and I'm going to do that right now. I'll pause. All right, I did switch the lines. I'm going to restart my program. Okay, everything starts at 0, and here I'm turning it one click, and that click is actually a mechanical detent. So there's something mechanical in there, probably a spring and a hole, that every time you move it one turn or one pulse, you'll see 18 degree change. So I guess it's because I didn't go completely one direction. Let me start again. 0. So here's 1, 2, 3, and so on until I get to 360 degrees, which is one rotation all the way clockwise. And now I'm going counterclockwise till I get to minus 360. And there we go. So I'm turning it one direction, the other direction, and we can measure this with the oscilloscope as well. So that's it for the LabVIEW demo. Part 2 of the lab has two methods of producing a square wave. One of them is to use the Arduino Mega as a device that's going to produce the square waves, and we're going to use pulse width modulation, and we're going to be measuring that signal on pin 45. Okay, so it's important that you use pin 45 when you do that, and you're going to be using a program that looks like this. So you can see here's the hardware. Pin 45 is going to connect to the digital I/O1 pin because that's the pin that measures signals coming in and will eventually tell you the frequency, period, duty cycle, and so on. So that's what we're going to be measuring. So we'll look at an example of that. And we'll start off with that method, but the second method is going to be using the TLC 555 timer, and we're going to take the output of that timer and connect it to digital I/O1. Okay, so you have to set up the timer to produce a certain amount of time high and a certain amount of time low, and I will also show you an example of that using a LabVIEW program. So we'll stop this momentarily. So this is the LabVIEW program. I'm going to turn on line numbers, just 1 second. And you turn on line numbers by going to File, and then Preferences, and then there's a Display Line Numbers. Click OK. And now I have line numbers on the left. Very useful when describing the program. So this program is designed to produce a pulse width modulated signal on pin 45 of the Arduino Mega. It's actually using timer 5. And it's not a very complicated program, but not all parts is it critical to understand everything on how it works. But it uses timer 5. And 5 has two control registers. This stands for timer control register, timer counter control register 5A and 5B. And these two control registers configure the way the timer counter 5 will operate. And we are using a 16 megahertz clock, and we're dividing that clock by 8. And that's going to give me a base clock of 2 megahertz. And you can see that it's a 2 megahertz base clock. 1 over 2 megahertz has a period of 0.5 microseconds. Now the next part, and this is the only part that you will have to change, is on lines 13 and 14. So if you want a clock signal that has a period, in this case of 1 kilohertz, or a frequency of 1 kilohertz, a period of 1 millisecond, you will have to put 2,000 clock cycles, because 2,000 divided by 0.5 will give you 1 millisecond period. And then the time high is going to be 500 times 0.5 microseconds to give you the time high. And the ratio of 5B divided by 5A gives you the duty cycle. So in this case, the duty cycle is 25%. So when we run this program, that's what I would expect to see being measured. And we'll actually test it out in just a second. So here I have my Arduino Mega connected, and I have to plug it in. Give me a second. So you do require a lot of USB ports for this lab, so it's great to have a USB hub, which I do. And I would suggest buying a USB 3 hub, so if you connect any high-speed drives, that makes things a lot quicker. So you can see here that I've connected, it might be hard to see, but that's connected to pin 45 on the Arduino, and I have to have a ground reference, only the ground. I don't need to connect to the supply. So I've got the ground pin on the Arduino going to the ground pin on the MDAQ interface board, and I have pin 45 going to digital I/O1. It's kind of hard to tell, but the first wire is 0, the second one is 1, and it's going to digital I/O1. So now we'll go back to the MDAQ software to have a look at that. All right, this is actually part 3 of lab number 5, where I'm using the Arduino Mega to produce a pulse width modulated signal. And this particular signal has a period of 1 millisecond and a time low of 0.75, a time high of 0.25, giving it a duty cycle of 25%. I'm measuring the signal on pin number 1. Okay, that's important. So the output of the Arduino, which is on pin 45, is going to pin number 1. And I have a program that's actually measuring that time. This shows you how accurate things are. So my time high is showing up as 0.25 milliseconds, time low is 0.75, period is 1 millisecond, and the number of clock ticks at 100,000. And that's giving me a frequency of 998 when it does the calculation, and a duty cycle of 25%. So the time high is measured when the signal starts on a rising edge right here. Time low is measured when the signal goes through a falling edge. Now let's actually have a look at the program. So I'm going to go to Control E to switch to the block diagram. And here's my block diagram. It's not the whole thing, so I'm going to shift over as we move along. I'll shift from left to right. So starting here, what we have is something called a flat sequence structure. It looks like a film strip, a 35 millimeter film strip. And to get that on the screen, I'll just show you how to do it. Okay, you right click on the screen, you go to Structures, and it's something called Flat Sequence. So you actually start to draw it just by panning it out. And then if you right click on here, you can add, and you can add frames after. Okay, it can be a little tricky moving these things around to make the space that you need, but it's right clicking on here and then add frame after, and then just adjusting the frame sizes. So that's where you'll be putting the code in each of these frames. If I right click on here and show visible items, I can actually label that. But I'm going to delete this. So remove, delete this frame. I guess I can delete each frame. Probably a way to delete the whole thing, but we'll there we go, remove sequence. So we start off with the first sequence. And what we have to do here is we have to have these in frames, because we only have one counter timer, and we want these things to happen in sequence. So what I'm doing here is I want to measure the time high and I'm going to do it in seconds and in milliseconds. To do it in milliseconds, I'm actually going to multiply the time that we have. I'm going to multiply the time that we measure in seconds by 1,000, because in seconds it will show up as 0.001, which is 1 millisecond. If I take that number, multiply it by 1,000, I'm going to get milliseconds. So you can see that I did that for each of these 3 frames. Now I'm going to open this up, and the other thing I want you to notice is I did put a time delay in here. So I'm giving it 100 milliseconds to measure, then move to the next frame. But let's open up. So here we want to measure the pulse width high. So how do we do that? We open this up. This just takes a second. You double click on it. Maybe I didn't, so I'll try again. There we go. So I get this configuration box, and we want to do pulse width. And I'll just show you by adding another one, but I'll delete it. Is that you have the choice of pulse width, edge count, and a whole bunch of other things. But we want to do pulse width for this particular operation. And when you get to pulse width, you're able to open counter 0, and you say OK. And then I have a second pulse width, and this is where you set up that we want to start on a rising edge. So we're going to be measuring the time high, and you also want to indicate the minimum and maximum times that you're going to measure. So my minimum is 1 microsecond, my maximum is 100 milliseconds. And the purpose for doing this is to set up the timer divide ratio. It does it automatically, but you have to specify the minimum and maximum time. So I'm going to delete this and show that I've got that pulse width set up, and I'm measuring the time high. So this first box, I'm measuring the time high, and it's giving me the results in seconds. And once you've done that, then you can just say, okay, I'm going to say cancel. So this one's measuring the time high. Then if I open up this pulse width, this is designed to measure the time low. And you can see the only difference that I have here is the starting edge is the falling edge. I'm going to cancel to that. And then this one is measuring the period. So there's another function that measures the period. So it's one of the functions that you can pull down. Period is between 1 micro and 100 milliseconds. And it comes up saying that's what I want to measure, the period. Okay, if I did this, I can click another one, and you can see period is one of the choices. But I'm not changing that. And then the next one, so I'm going to do cancel to that. The next one is the frequency, pretty much the same thing, except here if I wanted to add another one, it would be frequency, but these are all my choices. Okay, and then cancel to that. And then the next box, so let's just review quickly here. I'm measuring the pulse width of the time high, the pulse width of the time low, the period of the signal, and then I'm going to move along. So I've done those 3. And then the next are the frequency. And you can do the frequency, just open this up. I may have done that, so it could be repeating. And the minimum frequency is 2 hertz and the maximum is 10 kilohertz. You can change that though. Okay, and you can see that frequency was one of my measurements, so I'll cancel that. And I believe you can do duty cycle as well, but I did it in a different way. So I just took the time high, divided it by the period, and then multiplied by 100 to give me percent duty cycle. All right, and the clock ticks are a measurement of the base clock period. Okay, and I'll show you an example of that in just a second. Okay, so now I'm actually running the program, so it's live updating right now. You can see the loops, and these are the loops that are actually doing all of the calculations from that film strip thing that we looked on the other page. So it's telling me that the time high is in seconds 0.000251. So that's 0.25 milliseconds. That's where we're multiplying by 1,000 to convert it from seconds to milliseconds. And then we're doing time low, multiplying it by 1,000 to give it to me in milliseconds, and same thing for the period. I want you to do both. And the other thing to notice, and I'll stop the program for a second, but for example, in this box, it's not stopped. In this box, if I right click on it and do display format, you'll see that it's set up for floating point, and we want 2 digits of precision floating point and turn off the hide trailing zeros. It wasn't done prior, but that's the way I want it to be. And for the time high in seconds, we'll go to display format, and it will turn that off. It'll be 6 digits of precision. So it's going to measure down into the microseconds. So this actually is 0.25 milli, 0.000251 seconds, or 251 microseconds. Okay, so set that up appropriately. Same thing for the duty cycle and the frequency. We don't even need a digit of resolution here, so I could change it so that I have it as 4 significant digits. That works as well. Okay, so now that we've done that, let's run it one more time. And I've changed that so you can see the numbers that I have here. But what I'm going to actually do is change my Arduino program. So I'm going to come here. Okay, and notice the changes I've made here. So I'm making the period 4,000 times 0.5 microseconds. So that's 4,000 times 0.5 would be 2 milliseconds. And 800 times 0.5 would be 400 microseconds. Okay, so 2 milliseconds, 400 microseconds. I'm going to download the program. Okay, it's compiling, uploading, done uploading. Okay, now we'll switch to the LabVIEW program. So now my program is running based on those numbers, and you can see that the period is 2 milliseconds, as to what I expected. The time high is 0.4 or 0.4 milliseconds or 400 microseconds, and the time low is 1.6 milliseconds. So everything worked out the way I expected. So this is the final demo for now.